Welcome back, guys. Right now we are going to do 1.5 inverse functions. So we need to figure out the undo, and this might be new. This format might be new to most of you. This is what we call compositions, but the truth is with inverse, we know it's the inverse if it's invertible. So if g of f equals f of g. Okay, so verify the functions are inverses of each other. So in other words, I have to do g of f and f of g here. So let me do the first one. G composed of f of x. That's that first one. That tells me I'm putting f of x in place of the x for g. So I can write that as g of 1 over x plus 2. When I do that, and I replace that in there, I get 1 over x plus 2 minus 2. Okay, so remember that, oh, I didn't do this. Oh, watch, guys. So this is actually, I forgot the 1 over. So when you think of that, if I have 1 over a fraction, that's the same as 1 times the reciprocal, right? So that I can simplify as x plus 2 minus 2, which of course gives us x. Now, and that works, right? So that's awesome. This is good. So now, so I misinterpreted before, guys. It's that g of f is x and f of g is x. So they have to both equal x to be inverses of each other, okay? So I'm sorry for saying it. So let's do the other side. So f of g of x. Let's compose this. So that would be in f of x, I am placing 1 over x minus 2. This one's going to be a little bit more complicated when it comes to our algebra, okay? So let's replace it. So I have 1 over, now instead of x, I'm putting 1 over x minus 2, and then I have the plus 2. Here's what's great now. Maybe it's not as much work because these 2's cancel. And if you look, that gives us 1 over x. And again, dividing by a fraction is the same thing as multiplying by its reciprocal. So we end up getting x. So yes, these two are inverses. So f of x and g of x are inverses. So let's look at what this means. Okay, so they're invertible. Think about the function x squared. X squared has the domain of negative infinity to infinity. So is there a function that is the inverse of the function f? Well, we've run into an issue here, right? Because when we do the inverse, what happens is that we no longer have a function, right? Because a vertical line test does not work. So we have to keep in mind, if we want to test it, we might have to restrict the domain. Okay. So definition time. A function is said to be one-to-one if a function has an inverse that is also a function. Okay. So the way that we can do and test for one-to-one is graphically. We can do this with the horizontal line test. So, of course, if we have a graph and it passes the vertical line test, we know that function is a function, or that graph is a function. If we do the horizontal line test, that means its inverse is also a function. Okay, so what we're going to do here is we are going to test this ability here. So let's go back up to this definition. So 1-to-1, if and only if, whenever f of c equals d of c, then c equals d. Okay, so that's if I plug in c and d and what happens. Okay, so what we're going to do is we're going to show that c equals d when we plug them in both ways. Okay, we're going to do that first by using that definition, and then we're going to show graphically how that is. So here's our function. So on one side, I'm going to plug in c, and we're going to see if that equals d plus 2. All right, so now we have to solve. And remember, we're wanting that in the end, it comes out that c equals d, right? All right, how do you get rid of fractions? Well, you multiply by the denominator. So on this side, I'm going to multiply by d plus 2. And on this side, I'm multiplying by c plus 2. Okay, so that means that I have 2 plus d equals c plus 2. Now the denominators will technically cancel because I can put down here that they both equal each other, but then if you multiply both sides, they cancel. Okay, so it's just about the numerators at this point. So if I got rid of the 2 here, I'll subtract 2 from both sides. What do we end up with? We end up with d equals c. So check mark, and that shows us that f of x is a 1-to-1 function. Okay. Now I'm going to prove it to you graphically. Okay. So on a graph, we know that this is a rational function and that x plus 2 is on the inside of the graph, on the inside of x, right? So think of the parent function as 1 over x. So when we say 1 over x plus 2, that's on the inside, which tells us we go left 2. Okay, and this is just my side note. All right, so that means in a rational function, the parent function, we would have an asymptote at 0. But since we're moving to the left 2, my asymptote is at -2. And then if you look at a graph itself, it would look like this. Okay. Now, of course, that curve would look a little bit better. I'm getting messy with myself. So we can say, hey, it does pass the vertical line test. So vertical line test. Now we know that because we said f is a function, so it better pass it. Now we got to see if we do the horizontal. So if I start doing horizontal lines, now according to my graph, it looks like it would cross multiple times. But remember, there's that slight angle to the curve, so it does pass the horizontal. So that is why it's a 1-to-1 function. Okay. Let's test the next one. Okay. So let me get my pen. We're going to show that when we put c in there and d in there, that we can simplify it, that it comes out the same. Okay, so c squared minus 2c plus 4 equals d squared minus 2d plus 4. Well, obviously the 4's cancel, right? So let's get rid of the 4's. Now, how are we actually going to solve for this? Well, first of all, we want to move everything to one side. So we get c squared minus, and let's put the squares together, minus 2c minus plus 2d. You have to add it because we're going to the other side and set that equal to 0. Now, I want to show you guys something because this is something you might not think of. Right here is the difference of two squares. What does that mean? Well, difference of two squares, remember, is that means you can take the square root of both, and then we have a plus and a minus. So we have c plus d times c minus d. And then we have this minus 2c plus 2d equals 0. The other thing we can do now is we can take out a negative 2. So let me write that again. C plus d times c minus d minus 2 gives us c minus d equals 0. All right. What we're going to do now is think of this like factored by grouping. Okay. So remember, this is the first part, so we can put these two together. We can put these two together, right? Because those are common. Remember, we want that to be the same when factored by grouping. If you don't know what I'm talking about right now, what you want to do is leave yourself a side note that you want to talk to me what I'm saying about factored by grouping. So what we get is c plus d minus 2, that's the outside stuff, times the inside. Now the only reason why I can factor by grouping, guys, is because those inside ones are the same. So I only put that down once. Equals 0. Okay. Now, because it equals 0, I can take each part separately, right? So I can say c plus d minus 2 equals 0, and c minus d equals 0. Okay. Well, in this one, we get c equals d, and that's actually what we wanted, right? But the problem is here. When I solve, let's say for c, I get 2 minus d. These are two different values. So different values, which means necessarily that c does not equal d, not all the time. So that would indicate it is not 1-to-1. Now, graphically, because we're still kind of doing that graphical stuff. Now, okay, I'm going to give this to you. If we were to complete the square and all that stuff, that graph is a parabola. It ends up being up here. And yes, it's a function itself because it passes the vertical line test. But as you can see horizontally, it does not. Doesn't pass horizontal. Sorry guys, line test. Which means, again, it's not 1-to-1. Now for this one, you don't have a graphing calculator. So if you graph it, might take a little bit more of a trick. Maybe finding the vertex, things like that. Or you can do it algebraically. Okay. Now, properties of inverse functions. Because f composed of g of x equals g of composed of f equals x, we can observe some important things about inputs and outputs of this, okay? How it goes in and out. So some of the things that we can think of here is that the range of f, so let's point this out because this is good to know. The range of f is the domain of G. And that goes the other way around too. The domain of f is the range of G. So it's interchangeable, okay? And then we know that if f of a equals b, then g of b equals a, and vice versa. Okay, so if your other teachers haven't shown you this either, what's great about inverse is it's always symmetric to the line y equals x. So this is y equals x. That means whatever is on this side for one function, the inverse will be on the other. So as you can see right here, if I have f of x and g of x is its inverse, when we graph it, it reflects, it's symmetric off of y equals x. So let's make sure, remember this, I'm going to make this bigger. It reflects or is symmetric off of y equals x. Now, uniqueness. There is exactly one inverse function for f that is denoted by f of f to the negative 1. So keep that in mind. When we say inverse, you always want to end your answer with it equaling to f to the negative 1. And there's only one if there's an inverse. Okay. And then, of course, we have that reflection. Okay. Make sure that you remind yourself that f to the negative 1 does not mean 1 over f. Usually when we talk about exponents, right, we talk about it being in the denominator or switching numerator and denominator. But negative 1 is not an exponent. It's an indication that it is the inverse. So we have to keep that in mind, okay? So when graphing here, I'm going to get my ruler. We can sketch this just by having a graph because we can have the line y equals x, and then what we could do is just take the points and mirror it. Remember, it's opposite. So if this is 2, 1, this one's going to be 1, 2. If this one's very close to the y-axis here, then it's going to be very close to the x-axis. And then, of course, I might not curve correctly here, but so it mirrors. So graphing is nice because it gives us an answer right away. All right, so how do we find the equation, though? I get it, we can graph it, but how do we find the equation? Okay, so find the inverse of the 1 function f of x equals 2 minus 3x over 4. And graph y equals f of x and y equals the inverse. Okay, so one of the things that I want to show you is that we should know from the past that we can change x and y and solve. But really here, what I like doing first, no, I guess let's just switch first. So remember that this f of x is saying y equals 2 minus 3x all over 4. So the first step is to switch our x and y. So x equals 2 minus 3y all over 4. And then what we're going to do is solve. So I got to get rid of that denominator, and I get 4x equals 2 minus 3y. I'm going to solve for y now, so I get 4x minus 2 equals negative 3y. And then I'm going to divide by 3, so I get 4 over negative 3x minus plus, because of negative over negative, 2 over 3. Now, here's the tricky part. We have a habit to wanting to put y down because that's what we solve for. The truth is we solve for the inverse. So instead of y, I'm going to put f of negative 1 of x. Okay. Now, how can I graph that? We know how to graph a linear, guys, but of course, nobody wants to estimate, right? So here's the best thing to do. Let's just plug in points, right? If I plug in 0, I get 1/2. Let's try something that works out very well. If I plug in 3, that's 9, minus 2 is 6. So what did I do? Let's coordinate. Let's do 1. What did I do? Sorry, guys. I'm looking at my notes and I'm trying to figure out. But we can just plug in a point, if anything. Let's see. I'm just trying to remember what graph is what. Oh, I plugged in 1 down here. So let me do this one first. I plug in 1 here. I get 4/3, negative 4/3 plus 2/3. So let's plug in negative 1. Okay. Sorry, I'm doing some math in my head to get it to an even number, guys. So I see that it's in thirds, so I'm going to try to do a multiple of 3 on top. So if I do negative 1, I would get 4/3. So I go 4 divided by 3 plus 2 divided by 3. Okay, and that should be 6 divided by 3 is 2. Okay. So on this graph, at negative 1, I'm at 2. Which, by the way, I'm just looking at my work from last year and it's not making sense to me. Okay. Which means if we plug in, let's plug in here. If we plug in negative 2 here, what do we get? Plug in negative 2, we get 6, 8. Negative 2, we get 2 for this one. I should put this in another color. So I get negative 2, 2. Now, here's a great thing about that. Remember that since we have this reflection right here, my orange will reflect. Sorry guys, I need to pause for a second so I don't mess this up as I'm going. Okay, because my work from last year was wrong. We are okay. You guys agree with me on this point? Now the great thing is when we're doing an inverse, all we have to do is switch x and y. So if this one goes to negative 1, 2, this one must go through to negative 1. So I'm going to graph that. 2, negative 1. And of course for a line, all we need is 2 points. So I am going to graph that now. If you guys need rulers when you practice, I have stuff in the room. And for the orange right there, remember we had negative 2, 2. So on this side, we get 2, negative 2. So you guys see that? All I have to do is change x and y when I know it's the inverse. So 2, negative 2. Now, when we graph these, it should look like it mirrors off of the y equals x. Here we go. Oh, I feel better about myself right now. Thought I messed up for a second. So see, this top half mirrors this green bottom half, right? If I fold it, it would be the green and the orange would be on itself. Okay. Find the inverse of a 1 to 1 and use it to determine the range of the function. Oof, range of the function. Here we go. So first thing I'm going to do is switch my x and y. We know this is y, so I'm going to switch that. So it's x equals 2y all over 1 minus y. Okay. We have a denominator, so of course our next step is to multiply both sides by that denominator. Okay, so those cancel. We're going to distribute that out too, okay? I get x minus xy equals 2y. Okay, remember, what's our goal? Get y by itself. So the next step I need to do is get all the y's on one side. So I have x equals 2y plus xy. Now I can factor out a y, so there's only one of them. So y times 2 plus x. And how do I get y by itself? I divide. So I get x all over 2 plus x. Don't forget, I'm not going to put down y. I'm going to put f to the negative 1 of x. Now, remember what we said before, that the domain, so this is G, right? We're going to use it to determine the range. So the idea is the domain of the inverse equals the range of the first function. Okay, so we can conclude, oh, and this should be G, not F. Sorry, guys. Okay, so we can determine the domain here, and that domain is actually the range up here. Okay, so what cannot happen in this function? Well, x cannot equal -2, right? Because if it's -2, then it's 0. So the domain of G to the -1 of x, okay, let's keep that in mind. The domain is -infinity to -2, -2 to infinity, which means this is also the range of our original function. So they interchange. One last thing, guys. All right. So let's go back to that function that we knew was not one-to-one, which was that x squared, right? It did not pass the horizontal test, so it wasn't one-to-one. So what if we want to, though? If we want to find an inverse that works. So the idea is we're going to have to restrict the domain. Restricting the domain only gives you part of the graph. So this is our x squared, but if I say with it, we're going to restrict where x is only positive, then our parabola, we only have half of our parabola. Well, now does it pass the horizontal test? Yes, it does. And I can prove that to you, okay? So we would have, let's switch our x and y, we would have x equals y squared. And how do you get rid of a square? We take the square root, and there's always two answers, right? Now I'm going to put y here because we're not done. Because the idea was that we were going to restrict it to x only being the positive values, right? So that means that if x on G, or f of x, here we go, the original function f of x, then our inverse, the inverse of y has to be positive, right? Because remember, the domain and range, they interchange there for your inverses. So that means, since we are using this, that our inverse is only the positive side. And I'm going to show you how we restrict or how that restriction is shown. When there is a restriction, there will always be a comma and then an inequality. Okay, so it says graph the following functions to show that they are one-to-one and then find their inverses. Okay, so when you graph, the best thing to do is just to do a table, since we do not have a graphing calculator, right? So I have x and I have my y value. Now, x is less than 1. So my highest value is going to be 1. And I know I want to graph multiple coordinates, so that way I know what it looks like. So I'm going to graph 0 and -1. I think that would be good enough. Now, you're going to plug that in your calculator or do it in your head, one or the other. But when we plug in -1, we get 7. Plug in 0, we get 4. Plug in 1, we get 3. Okay, now I'm going to graph it. Of course, my graph's going to be a little bit off because, as you can see, I am not really being so neat with my graph right now. So at negative, let's go down here. 1 is 3, 1, 2, 3. 0 is 4, and then -1 is 7. So as you can see, my graph is the left side of the parabola. Does this pass through the horizontal line test? Yes, it does. So now what we are going to do is change our x and y. And solve for y. Okay, now I stopped here, guys, because we would have to change this to vertex form and then solve for y, or we could do the quadratic formula and solve for y. That gets a little bit complicated here. So if you run into something like this on your homework, please call me over and we'll go through that. But I don't want to go through completing the square right now because we will be doing that later on in this course, okay? So we're going to do this graphing in Algebra 8 down here, okay? So let's go back. There are no restrictions in this one. No restrictions whatsoever. So if I remember my transformation, this is going to go left 2, down 1. So left 2, down 1, and it's a square root, so it's kind of that curve. Okay. Now, does this pass our horizontal line test? Yes, it does. So let's solve this algebraically. X equals the square root of y plus 2 minus 1. Okay, add 1 to both sides. How do you get rid of a square root? You take the square of it, so x plus 1 squared equals y plus 2. And then if we want, we can FOIL that out, which comes out to x squared plus 2x plus 1 equals y plus 2. Move that over, we get x squared plus 2x minus 1 equals our inverse. Now, here's our problem. Even though it didn't say there was a restriction here, the reason why I didn't need to say it is because there was already a restriction. Here, this is a parabola, so we had to restrict it. Down here, though, there's already a restriction in place. What can't happen? Well, the domain for this one says that x has to be greater than or equal to -2. If we plug that in to find the range, on this one, the range, if I plug in that -2, y is greater than or equal to -1. What does that mean for down here? Well, that means the domain here is x is greater than -1, and the range is y is greater than -2. Okay? So keep that in mind, they switch. And just because this is a function here, remember, we only start out with part of the graph here. So there's only part of the graph here. Do you guys also see, before I let you go, that I had this in a vertex form here, and then I made it to standard? Where here, and this is why I didn't do it yet, is because this is standard. We would have to complete the square to make it to vertex and then solve. Again, if you run into that, call me over. We'll talk about it, but I don't want to get you in the square, completing the square yet, because we're not there. All right. Enjoy your day.